we'll continue our study of problem decomposition by recursion. And if we recall that we had decided that our problem will be written in a recursive manner by a principle in which we have got two parts, the base condition and the inductive conditions. The base condition specifies what will happen on the boundaries of the recursion, and the inductive condition specifies the problem decomposition. And in the problem recursive part, we had two aspects of it. One was the decomposition part of the problem, the other was the recomposition part of the problem, and together they form what is a well-known technique in computer science, and is called the divide and conquer principle. And we saw several simple examples informally of how to do it. We'll just quickly go back to a more reasonably written version of those examples. The first was the simplest one, in which we had the factorial program, where the base condition was when n is equal to 1, the value is 1. Otherwise, this was the decomposition, fact of n minus 1, and the recomposition was n into the return value of the factorial. So this was the decomposition and this was the recomposition part of the problem. Next, we tackled the Fibonacci numbers, and in the Fibonacci series we saw there are two base conditions. When n is, it was called with fib n, and when n is 0, the value is 0, when n is 1, the value is 1, and these two together form the base conditions. And unlike in the factorial, where there was only one subproblem to be solved in the decomposition, here we had two subproblems, fib n minus 1, which we called recursively, and fib n minus 2, which we called recursively. We got back the two solutions and we recomposed it by adding the two of them. And this is what we returned as the value in val. Then we saw the Tower of Hanoi's problem, which when written down had got n disks on 3 pegs, and they were called from, to, and via. And to solve the towers problem, you had to transfer these n disks from this peg to this peg using this peg. And these are the 3 parameters which are character inputs in our case, and n is an integer. But what does it return? It returns a list. It returns a sequence. So it returns a sequence of numbers, of moves. And a move was represented by a tuple of the form and say 2 moves were represented like this. So this was the sequence of moves which we used to represent the solution. So what it must return is a list, unlike in the previous 2 cases, which was an integer. And let us remember that list is no defined data type in a language like C. But when we design the problem, we design it using our own mental structures, and as we know, it's a sequence of tuples, or we call it a list of tuples. And the base condition was when n was 1, L, which is the returned list, is only one element called from to to. And the inductive conditions were when n was greater than 1. And there we broke it up into 3 subproblems. First, we said that n minus 1 from this peg, we'll move it to the via peg using the to peg. Then we will move one disk from the from peg to the to peg using the via peg. And then we will move the n minus 1 disks back. We had moved it to the via peg, we'll move it from the via peg, and we are required to move it to the to peg from the from peg. And we will get, for this we will get a set of solutions, for this we will get a set of solutions, and for this we will get a set of solutions. And the final solution will be an appending of these 3 lists to form your list L. And this is the recomposition of the solution. And we return L, either computed here or computed here. Is that okay? So this is, now we have written it down in a much more organized fashion. The next was the merge sort, the split sort. Here again, the input L is a list of integers. What is returned is another list of integers. And we have got the basis condition when n is equal to 1, the returned list is the same as the original list. That is, when one element is there, it is already sorted. In the inductive condition, we split L into two non-empty lists, L1 and L2. And we recursively merge sorted L1 to get L1 dash as a returned sorted list of L1. We recursively sorted L2 to get a sorted list L2 dashed. And we defined what was a combined routine which could combine two sorted lists to form a complete sorted list. And let us now call it the routine merge, because this is what it is traditionally called. So these were the decomposition steps, splitting and recursively merge sorting, and then the recomposition of the solutions by the function merge, and the list L dash is returned. Is that okay? The other version, which we called quicksort, which was a slightly different variation. Here again the input is a list of integers, the output is a list of integers. N is the size of L. If n is equal to 1, the base condition is same. Otherwise, we selected out one element of L and we created two lists. One is L1, which puts into L1 all elements from L which are greater than or equal to X. This is what split GE does. Split LT does what? It returns a list L2 which, taking the list L and the element X, returns all elements which are less than X. And then we quicksort L1 by the same algorithm. We could have used merge sort here also, any sorting routine, but we will recursively use quicksort. We are doing problem decomposition. And L2 to get L2 dashed, L1 to get L1 dashed. And now these are sorted, both are sorted, and they are placed such a way that if we want to put them in ascending order, we have to just put L1 first and L2 second. So we append or concatenate L1 dashed and L2 dashed and recompose the solution. So this is the approach that we used. We have just written them down in a more organized step-by-step fashion. So here again we have the decomposition steps and the recomposition step. Now what's left? Is this the end of our programming? So the next thing we have to answer is how to convert these definitions to programs. And before deciding on this, we have to answer several issues. The first is, before converting to programs, we have to answer several questions. The first question is, what do we do with the data structures? Whenever there is integer, etc., there is no problem. But if we end up with things like list, we have to implement this list. With integers and characters and an array, how will we implement a list is something we have to answer. Or will we do it in some other way? We have to return a list of what? A list of pairs of elements. How will we logically pair up these elements? So how will we write out our program for describing these lists? Here we have just informally written them down. So we have to write down, we have to organize our data in form of higher level structures than pure integers or characters or arrays as they are given. So this is a part of data structuring, the simplest data structuring, which we shall have to address. The second question which we will have to answer. So first is directly how do we convert it to programs. So we'll have to answer this question and we'll see what we will do at each and every place. Second is what do we do at choice points. Now let us see what choice points we had. Split a list into two non-empty lists L1 and L2. Where do we split the list? Half, 1/3, 2/3, or all are equal, or anything? Does it make any difference? We have got a choice of splitting here. What do we do? Does it have any effect? We have a choice of selecting an element L here. Which element do we select? Does it make any difference to the final algorithm if we select this element? So we have to answer these questions. We can do it arbitrarily, but as we saw in our example of max and min and max and second max, a deeper analysis really helps to get a better understanding of the solution. So we have to answer what we do at choice points. And in order to answer that, this is what we have to do. We have to analyze this initial definition, as we call it, and do a complexity analysis. Complexity means how much time will an algorithm take if we take this choice point, if we take that choice point, if we use this data structure for a list, if we use that data structure for a list. What are we going to do? So unless we do this, we are never going to reach our required goal of getting the best possible solution. And only after we have done this, we have made two things. We have been able to choose the final algorithm by choosing what we do at various choice points, and we will be able to design our final data structures. How do we implement that list? How do we implement those elements from and to those pairs? Which is the best way to design them? So after having come up to this point, we are ready to design the final algorithm and the final data structures. And it is at this point that we turn to writing out the final program. It's a long way to go till we proceed to do this. And we have not yet learnt many things to proceed even beyond this point. So with the possible knowledge that we have at present of arrays and other things only, integers and arrays, we'll see how we can convert these definitions to programs at the level that we are in. And once we have got an initial working program which is correct, then we will go step by step to understand what we have to do here, what mathematics is involved to do this complexity analysis. But before that, we have to learn some more of programming. So today we will quickly see how we can convert these definitions to programs with whatever knowledge we have, and then we will see what other knowledge we require to see other avenues, and that's what we will study in the subsequent classes. So today we will just quickly go back and see the programs that we had. The factorial one is obvious, so we'll just pick the Fibonacci number, which is equally obvious. If you have to directly convert it to a program, there's nothing. You can just simply write this down in C language and you'll get a working program, because this is going to return an integer, and whatever we have in our knowledge, we can simply convert it into a program. There's nothing to do. We can directly convert it into a program. We are not analyzing the program to see whether this is the best possible, whether there are any choices we have. That we'll come to later. But today we'll just see how to just directly convert it to a program, and this one is obvious. So we'll see a slightly different variation of this. So here is the Fibonacci program. We have the main program. Is this visible? So we have the main program, and in the main program we just read in n, and in the printf function itself we call fibn. That's possible in C. And this is the fib_n program, where fib_m actually, this is the parameter. Base condition, if m equal to 0, return 0, else if m equal to 1, return 1, else return. I have just written out a more compact program just to show you the way it can be written in C. Fib_m minus 1 plus fib_m minus 2. So this will give you a solution. Even if you had written fib_m minus 2 plus fib_m minus 1, even that would have given you the solution. Both are equivalent. So you could have, this will return you fib_m minus 1 plus fib_m minus 2. In a return statement, you can put in an expression. And if you just run this, it doesn't ask for n. So fib5 is 5, fib6 is 8. So whatever you do, you will get it. Just a point which I wish to mention here is that if I replaced this by 2 and this by 1, even that would have been correct. It does not matter if I do fib_n minus 2 first and then m minus 1 second, because both are independent subproblems. This will return one solution, this will return another solution, and the solutions will get added. This is because addition is a commutative operation. Because addition is commutative, you can do any one of them in any order. So if I do it in any order also, I will still get the correct solution. So that's fine. So I think that's quite easy to understand if we do this Fibonacci problem. So let's come to the Tower of Hanoi's problem. The first problem that we encounter here is a list. We have to return a list of elements. We still don't know how to return a list of elements unless we declare an array. We can declare an array for the solution, and this can return an array. Alright? But do you know the size of the array that you have to declare? What is the solution? If for Tower of Hanoi's of n, the total number of moves is so the size of the array that you have to declare is exponential to n. Anyway, you can declare an array and put the solution and return an array, and I leave you to decide to find out in C language how you declare an array to be returned from a function. And then you can declare 3 arrays, and based on these 3 arrays you can write an append program to combine 3 arrays into another array. Alright? Now if you implement it using arrays, one very interesting point, like in the Fibonacci numbers, if I did this one first or this one second, it does not matter. If I take back the solution and I do L1, L2, L3, does it matter if I do this one first, this one, if I write it down in another order? I have to just do this append in the proper order. If I do the append in the proper order, I am going to get the solution. Is that okay? Now I'll just take a different approach to using a list. What I will do is, instead of using a list, I will just print the solution. If I will not return anything. Tower of Hanoi, here, if n is equal to 1, it will just print from 2. I don't want to use an array of such a huge size, I just want the result to come on the screen. So, if n is equal to 1, instead of L is equal to this, it will just print from 2. Otherwise, it will recursively call this one, recursively call this one, and recursively call this one. This append is no longer required because the solutions are printed from inside. But once I do that, it becomes very important to write these 3 in proper order. Because if I write them in reverse order, then since the append function is not there and printing is done inside the routine, it will work out in the order in which I ask it, I give it to the recursion. Is that okay? So if I have to just simply print it, then I will call this, and call this. And instead of this append, I'll have nothing, and instead of this, I'll just have a print. And that will solve my problem. We'll go back to using a list when we see, is this the best way to solve this problem or not? When we have to answer this question, we will come back and see something else. But now, whatever knowledge we have at our disposal, we'll just use it to write a program which works. So let's see how that program will look like. The main program is here. N, it reads in N and calls tower N, A, B and C. And this one is the towers routine, which takes in an M as an integer and 3 arguments as I mentioned before, and we have declared them to be characters, because if you will notice I have called them with characters A, B and C. We are introducing characters possibly for the first time in this course, but I think this part is quite clear and obvious. So we can declare characters by the word char, and these are all single characters. From is one character, to is one character, and via is one character. And if M is equal to 1, what did we say? We will write a print. Printf move from %C is the format to write a character. So move from %C to %C, and the first one is the from and the second one is the to. Or else call towers recursively from, via and to. And this one you could have called it with M equal to 1, but I have just written out the M equal to 1 case specifically here again. I have just repeated this statement here instead of calling M equal to 1, which is the same thing. And here I have called towers via, to and from. So this is the recursive, direct recursive version of the towers of Hanoi, where the list input is not taken and we just print the output. And we have to be very careful so that we do it in this particular order, because if we do it in any other order, we will get the problem solved in a different order, because recursion will first do this, then do this, and then do this, and inside it the printing will take place. So suppose you give 1, you get this. You give 2, A to C, A to B, C to B. You give 3, you will get the 7 moves, and similarly if you give 4, you will get all the moves. So let's quickly go back and see that doing it this way really gives the solution instead of writing out lists and all that. Do I need to go through the recursion once, or is it okay? Okay. So what did we have? We called it with 3, A, B, C. And the recursive program, I'll use this to highlight the recursion. We first call towers n-1 from, via, to, then we print it, and then we do this. And in the base part we directly print it. So let's see how it works if we do it that way. Exactly how the program executes. So first this part will get called to A, to C, to using B. So the call will get transferred here. So this will again start executing. So this starts executing. It is not that independently these are 3 called. So this starts executing as recursion goes. So 1 A B C from to via, so the first call is from via to, and this starts executing. Now this is a base condition, and what happens? We are supposed to return this. Instead of that, we are printing this. So first we print A, B. This gets printed. Remember, this was going to be appended in the beginning of the list, because this was going to get appended, then something, that was going to come back here. And so this would have come in the beginning of the list, and this is going to get printed first. Then, so once this completes, the second part of this executes, which in our program, instead of calling one this, we simply printed AC. Remember, if we called it recursively also, AC would have been returned, and AB would have been the first element here, AC second, this would have come back here, and AC would have been the second element in the solution, and AC is going to get printed now. Thirdly, we are going to call 1 C, B to C using A. This is what is going to happen via to from. The second recursion is via to from. Via to from. This is from, this is to, this is via. So via to from. So after the control, initially it came here, then it came here, then it came here, then it came here. And so what will now get printed, because this is a base condition, B, C. And then control will go back, this part is done fully, goes back here, and the next subproblem is generated, which in our case is 1 ABC, which is print AB. Then this part goes back, control goes back to this side. And the new subproblem that is generated is to via to and from. This is an inductive condition. So you get a recursion call is made, 1 C A B. You are here, so the control now comes here. This is a base condition. This gets printed. So then control goes back, and the next subproblem gets generated. C B gets printed, because 1 from 2. So CB gets printed. So this part, control goes back here, and the last subproblem for this, which is 1 via to from, and this is generated. This is a base subproblem, so this gets printed. This completes, control goes back here, this completes, control goes back here, this completes, control goes out, and you've got your solution. So this is how we have used recursion to solve this problem, where the list, instead of the list, we simply printed the solution out. Alright, so control over recursion is very important. You must understand exactly how recursion works in order to convert your problem into recursion. On the other hand, if you had used arrays, it wouldn't have mattered in which order you solved them. but it matters how you recompose them. The recursion that we have implemented, here only the recomposition automatically takes place by printing. So we have used recursion to solve the problem not only of decomposition but also formation of the solution with our knowledge of recursion. So problem decomposition and recursion in programming are not identical. You have to be careful and you have to use recursion to solve your problem. Therefore, the towers of Hanoi solution which we showed on the computer just now is a method by which we use recursion to solve our problem. We're out of time today, so we'll just see how quickly in the next class how we will solve the merge sort and the quick sort problems, how we will implement the list, and then we will have a discussion as to what we can do about this. So we are now trying to get some initial solutions, and once we are able to do that, we'll understand what we lack in terms of programming facilities, and we'll acquire them quickly, how to form a list, how to form structures of elements, and then we will be able to solve these problems and analyze them better.